Let's continue. So it's a pleasure to introduce Higinio Serrano. And Higinio studied mathematics at the Instituto Político Nacional in Mexico. He did a PhD in Simvestar, Mexico City. I had the opportunity to guide him in the PhD. And now he's a postdoc in the Institute of Computation and Mathematics, Mathematical Sciences, International Center of Mathematical Sciences in Sofia, Bulgaria. So he'll tell us about magnetic field.
Thank you very much. Thank you to all of you for being here. Thank you to Bernardo, to Emil, and Rafael for organizing this event. I have learned a lot of things from you, all of you. Thank you very much. First of all, let me apologize because I'm not a physicist and I don't understand a lot of concepts in physics, but I'm trying to get used to this. So I'm trying to close this gap, right? Instead of trying to close the gap between the physicists and the mathematicians. Also, I would like to explain that physicists and mathematicians try to, well, we have different perspective of the things, right? Because I see that, for example, physicists start with an experiment or with a model, right? With a computational model, and they look something interesting, right? And then you try to classify this thing or model of an invariant which tells you that we have something. We have some insulator which is not normal insulator, or we have a conductor which is not a normal conductor. But on the other hand, mathematicians like me, algebraic topologists, we take the space of all these things, right? And we would like to classify all these things. And sometimes we forget about specific models, right? So our work tries to first take the space of all possible Hamiltonians in a Hilbert space, cook the invariants, the topological invariants, and then we will try to cook all the Hamiltonians that model these invariants. But we are just in halfway. We have just, at this level, we have just computed the invariants of these spaces, right? So let me tell you this. Okay, here is something that all of you probably have been seen before, right? The classification table of the superconductors or the topological insulators, right? Here in this talk, I will focus more or less on these three categories: A1, or A2. The ones which contain time reversal, which square one, which squares to 1 or -1, right? Depending if you have spin or recoupling or not. And you know that there are some invariants, right? Depending on the dimension and on the symmetry, you have 0, C2, or C topological invariance, which tells you that in fact you have something and you know how to compute these invariants, right? We would like to have such a table for different symmetries. What if you have a material which contains a symmetry, well, which doesn't contain time reversal symmetry, but contains, for example, a rotation followed by a time reversal symmetry, or a mirror and time reversal symmetry, right? Of course, we will obtain new invariants. I will show you how to compute these new invariants. So let me recall you a little bit of why we consider unitary and anti-unitary symmetries. If we start with H, complex Hilbert space, we can consider this PH, which is just the space of one-dimensional subspaces of this Hilbert space. And we can consider this group the quantum automorphisms of this space. What is a quantum automorphism? It's just a bijection which sends lines to lines and which preserve this probability measure. For example, right, if H is just the complex numbers, this is PEC, okay? And one also has this the quantum automorphisms of the Hilbert space, which are unitary or anti-unitary operators of this Hilbert space. And it's a theorem of Wigner that if you have a quantum Hilbert space, then there exists this exact sequence, which means the following. If you have such a bijection, which preserves this thing, well, this bijection is modeled by unitary or anti-unitary operator. And if you have two operators which model one of these, they differ by a phase, by a complex phase, right? So in these quantum systems, we will model symmetries using unitary or anti-unitary operators. How we model these invariants? We will model using K-theory. In this talk and in my work, I just work with topological K-theory. I don't work with sister algebras. I work with the K-theory of topological spaces. Here I will be very briefly defining these things, but in some slides I will be more specific. So my main ingredients are complex vector bundles, okay? Here typically X is a compact topological space, which could be a torus or a sphere. And I consider complex vector bundles of finite rank. Which type of symmetries I consider? Well, I consider magnetic symmetries. Which are these symmetries? Well, I will consider finite groups, which can be at linearly or anti-linearly on the fibers of the complex fibers. And then I will consider this thing called the K-theory of, well, equivariant magnetic K-theory of the topological space, which is just formal differences of these complex vector bundles. Okay? This has some advantages. In what sense? In the sense that it is easy to compute, right? But the disadvantage is that we don't have a specific way to construct the Hamiltonians. We just compute the invariants, but we don't have a clear way to compute the Hamiltonians. Okay, so here I have the magnetic group, which comes with a map to this SIMO2, and it just tells us if an element of the group goes to the non-trivial class, it's because it acts anti-linearly. If it goes to 0, it will act linearly on these complex vector bundles. Okay, before I go further, let me recall a little bit of this, for example, alter-magnet effect. In a paper with Rafael and Bernardo, we take this model, this Hamiltonian, and we show that this spin upture number is a good invariant. It's a robust invariant to measure this non-trivial topology of this Hamiltonian. Okay? But it seems to be very ad hoc, right? Why this is a robust invariant? Why is topological? Well, we show also that this invariant comes from a class in the K-theory of the Lilloan torus. with respect to this symmetry, C4T symmetry. Another example is this in another paper, which they consider the so-called action isolators. They show us how to compute this thing, this theta term. Okay, this turns out to be also a good invariant, topological invariant. But you see, it seems very difficult to compute, right? And also, it's not so clear why it's robust invariant. But Bernardo shows that this invariant can be computed in terms of, again, a class in K theory. Well, he uses real K theory. This was before we coined the magnetic groups into the scene. But this real K theory is just a magnetic K theory of the torus, three-dimensional torus with this symmetry, C2, 3, with some twisting. I will describe all of this in the next slides. So, in summary, we know that some materials, some Hamiltonians have symmetries, and we would like to cook good topological invariants, robust topological invariants, like the non-triviality topology of these materials, right? And we have seen that some of these invariants came from places in topology. In K theory, sorry. K theory seems to be a good thing to classify these things. Okay, so let me give you a very brief introduction of the groups that we work with. So we work with space groups or crystallographic groups, or whatever you prefer to call it, right? What is this? It's just a sub extension of this, right? Of the Euclidean isometries of Rn. This is, as you know, it's called the point group. This is the space group, and this is the translation pattern, right? In our work, we just deal with simorphic groups. We uses this that we can split the point symmetries and the translation symmetries. Okay, now I will define in more precise terms what is a magnetic group. A magnetic group is just a group together with a homomorphism, epimorphism to C2. Why is this homomorphism? Again, it's just to keep track of the elements of the group which will act linearly or which will act anti-linearly. So for the next slides, we will consider finite groups of this group. This similar to model the time reversal symmetry. Okay, some examples. For example, if we take a finite complex vector space, we call the magnetic general linear group the group of linear or anti-linear isomorphisms of this complex vector bundle. And this comes with a natural map. If we have an operator, we send this to 0 if it's linear, or we send this to 1 if it's anti-linear.
Sorry, Higinio, your general definition of magnetic group is any possible group which is mapped to
yeah, this is the general definition.
Okay.
Yes. But for this work, we will focus on this type of.
With finite or infinite?
For this work, with finite.
Okay.
Well, of course, you can consider Lie groups, for example.
So then what's the difficulty for non-symorphic groups?
Yeah, we don't have.
So, but you will define the magnetic group the same way, isn't it?
Yeah, you define this definition works no matter if you have symmetricity or not. Okay.
So just the calculation.
Yeah, just the calculation. When you take the quotient of the R3 by the translational part, so sometimes is if we don't have symmetricity of the space group, then we need to consider weird twistings, the K theory, and we don't want to be still with these things. Okay, anyway, I will give you more examples of these magnetic groups. And of course, we need to speak about representations because we will build these invariants from complex vector bundles, but these complex vector bundles are built from these representations. So if we have a magnetic group, a representation of this magnetic group is what you imagine, just a homomorphism. But now we allow that our operators are linearly or act linearly or anti-linearly in the complex vector space. So, for example, if we have this finite group, sim of 8, which this is just an abstract group, but for example, it can model a rotation of degree 8 composed with time inverse symmetry. The generator, this will be the generator. If you consider this group, then you can speak about the representations of this group, and also you can speak about irreducible representations. It turns out that for this group, these three representations are all the irreducible representations up to isomorphism. But you see, this is one-dimensional, and these two are two-dimensional. This is different from the representation theory of just groups, because if you have a abelian group, finite abelian group, all its irreducible representations are of dimension 1, right? But here is not the case. Here we can have a reducible representation of dimension bigger than 1. And if you consider, for example, the action of this element, this will be this will look like this, and this will look like this. And in this case, we call this a reducible representation of real type, quaternionic type, and complex type. This is a general result given by Wigner. If we have a finite magnetic group, then there are three types of irreducible representations. This is the Schur lemma in this context. This is different from the Schur lemma in the classical setting, let's say.
And you get that because you kind of double the representations of C4, isn't it? The reducible representation of C4.
Again?
You get that because you kind of double the irreducible representation of C4.
You have this because of the following. You have a magnetic group which comes with a map. You can see the kernel of this map.
So in that case, C4, isn't it? C4.
Yes. But if you have any finite group, you can consider this. Consider the irreducible representations of this classical group. Classical. And Wigner gives us a way to promote irreducible representations of this to irreducible representations of this. In the real case, you just put one copy. But in the quaternionic or in the complex case, you need to put two copies, as you see here. One and the complex conjugate, or two copies of the same representation. It depends on the
So
type.
each representation of G0 leads to 3 irreducible representations of G. Is that what you're saying?
Well, it depends. It depends on the group. It depends. For example, for this group, we have the 3. But for example, let me give you more examples.
That's just one.
For example, for this
So I
group,
need two. One.
for example, for this group, see, the generator is C2P. Here we have just one irreducible representation, and this is of real type. For this other group, C4T, we have two irreducible representations. One is of real type, and one is of quaternionic type. And for this other, for example, group, generated by these two elements, C2 inversion and time reversal symmetry, we have two irreducible representations, and these two irreducible representations are of real type. So if you give me a group, a point group, I can give you all these representations, and there is a way to put in a computer, I think, how to cook all these representations. Okay, so let me give you now. Let me talk about the complex vector bundles. So if I consider again a magnetic group, what will be an equivariant vector bundle? Well, a equivariant vector bundle will be just a complex vector bundle over a compact space, which for this condensed matter physics will be just a sphere or a torus, which complex fibers of finite type dimension, and we will put an action on the base space and on the fibers. But now the action can be linear or anti-linear, depending whether the element is in the kernel or not in this structural homomorphism. So we can consider as a mathematician, no? Right? Why not? Instead of all possible vector bundles up to isomorphism, we would like to classify this. I would like to tell you what are all the possible vector bundles, but in real life this is impossible. Well, for example, for spheres, there is possible to tell you. But in general, for torus or any other compact space, it's almost impossible. So there is a standard procedure given by the K-theory. K-theory will give you information about all the possible vector bundles that you can consider. So as I told you, you can consider this group, which will be just the difference, the formal difference of vector bundles with actions of these magnetic groups. It will be generated by this. So the K-theory, for example, of one point, it will be the ring group of the ring, of the representations of this magnetic group. And we have shown that in general, this thing, the K-theory, the magnetic equivariant K-theory, is a generalized homology theory, which is aperiodic. What does it mean? It means that we have a lot of tools to compute this thing. And also it's aperiodic as in the real case. We have shown this, that if GR is a magnetic group and acts trivially on the space, we have this decomposition. So this K-theory will split as real, complex, and quaternion K-theory. For example, the K-theory of this group is the real K-theory in the sense of opinion. Okay. Let me give you. Okay. What about the spin-orbit coupling? Or what about twistings? I told you that we will consider that we have considered magnetic groups which lives inside here, right? But what if we have this term? What if we turn on the spin-orbit coupling effect? Well, we need to lift the symmetries to this group, to the double cover. As a mathematician, we will tell you. What does it mean in real life? the time reversal operator will lead to a operator which squares to -1. And for example, rotations of order n will leave two operators which the n power is -1. This will be the twisting that we will consider in our phone call. So for
Rotation symmetry.
Do it again.
For example, if we just consider time reversal operator, the leaf of this operator will be modeled by this group. And if we consider the magnetic group with spin orbit coupling, we need to put this twisting here. And this turns out to be the quaternion K-theory. I will give you more examples. Okay. I will tell you a little bit more of twistings. There are two ways of considering twistings. Well, there are more. I will tell you today two ways, and tomorrow Bernardo will tell you a third way to consider twistings of this K-theory. Okay.
You didn't know.
If we consider a finite group of U1, we can consider a two-cocycle. A two-cocycle is just a function with this group to A, which satisfies the boundary condition. I don't want to tell you about this. Or we can model, instead of having a cocycle, as an extension of the original group. This will, mathematicians prefer this model. But if we want to actually do calculations, it's better to work with with extensions of groups. Because we want to consider now twisted representation theory. What is a twisted representation? A twisted of this group. There are two ways of defining, two equivalent ways. One is to have a map from this to the magnetic general linear group of a complex vector space, which is almost a representation up to a phase, a complex phase. This is one way to define twisted representations, or the other is, instead of having maps from here, having maps to this big group, which are honest representations. These two definitions are equivalent. But this is more useful when we.
But you need the kernel to act. Maybe.
Yeah, you're right. This such that row of, let's say, G acts as scalar multiplication.
That's when G is in count.
Then G is here in the kernel of this. So we can consider twisted representations. We can consider also twisted vector bundles using this definition. So we can define the twisted equivariant K-theory. This is the space, the symmetry, and here it depends. You consider spin orbit coupling or not. Okay? You can turn on or turn off this term. Tomorrow, Bernardo will tell you more about this. So, for example, here I have some examples of twisted representations. If we consider the spin orbit coupling of this group, then it has again one representation of real path. This is the representation, just conjugation. Or if we consider this group with both with the spin orbit coupling effect, now we will have one representation of complex type. Before, I showed you that if we don't consider spin orbit coupling, we have two representations, one of real and one of complex type. But here is different. Also, here is another example. Again, there is an easy way to compute all these things. All these are reducible representations. And how to tell you how what type is this are these. So we prove this following theorem that if we have a magnetic group, then the K theory of the point looks like this. And here I have.
What are the ends?
Sorry, the NR, NC, and NH are the number of reducible representations of real, complex, and quaternionic type of this magnetic group. So here is a table which is an analogous of the classification of superconductors or insulators. But when we have the symmetry, C2T, C2T with sock, C4T, C4T with sock, so on and so forth. We can produce now for free these such a tables, and these are of periodic A.
But here there's no space, just a point.
Yeah, just a point. Just a point, but well, if you consider this the dimension, you can say, oh,
Then
is it
with trivial action.
Oh.
Usually the action is non-trivial. It's symmetries.
What if we don't have just a point? Why in the real life we have spaces, right? Okay. For example, now I will show you very briefly what happens if we have a space. If we consider the torus, two-dimensional torus, and this symmetry, C4T, which act on the torus like this. Here we are in the momentum coordinates, okay? And we consider also the spin orbit coupling effect. Here are the invariants of the torus. Notice that here we have periodicity 4 and not 8. And one other weird thing, for me at least, you look at these groups, C to the 4, C2, this group. But if we take this and shift by 2, we will have this and this and this. You see, there is a pattern. The first row is very complicated to compute. The second row, it's very easy to compute. Here, I don't know why, but maybe you know why. There is this phenomenon that we have the same invariance in the spin orbit coupling effect and without the spin orbit coupling effect, but we have shifted by 2. Maybe this is because there is some inequality kindness. Let me give you a very briefly explanation of how to compute these things. I told you that this K-theory is a equivariant homology theory, so we have a lot of tools to compute this thing. For example, here I will show you the spectral sequences behind this. Something very similar to what Tom told us. It doesn't matter. Here we have a bunch of terms. The important thing is this, that this C2 comes from this, and this comes from the 2 cell of the space. We can ensure that this invariant comes from the bulk. This is a bulk invariant, just because we can keep track from the spectral sequence, this C2 invariant. Yeah, and we are working on more symmetries. Here I just show you this K-theory with this symmetry, but we can produce more of these tables. Yeah. So this is, thank you for your attention.